when we stretch out that spectrum of models from the low-cost, high-error models to the high-cost, low-error models, we find some patterns in the kinds of models that live along that curve. At the left end, we have unarticulated wisdom, or sometimes what's called tacit knowledge, or what in engineering we call engineering intuition. And on the right, we have equations of motion, like Newton's laws or Maxwell's equations, that give very definite predictions of how the system's going to behave. In the middle, we've got different types of model. On the left, we have articulated qualitative models. Those can be verbal or visual. And then we start to move to the right. At some point, we cross a divide between those models that are qualitative and those that are quantitative. And so we move to models that are numeric in some sense, that have number associated with them, things like dimensional models, or models that model explicitly one facet but leave out other facets of something that of a system. So something we might call facet-wise models, over to the equations of motion that Newton set into play. The point here is that there's a trade-off, and that what we're trying to do is adjust models so that we use them appropriately. Now, what are models used for? They're used for many different things. They can be used to describe the way things are or were. They can predict the way things will be, or they can prescribe or describe the way things should be. And key variables here can be time and the way in which things would change from the current situation. Usually we're assuming that there's something out there that we need to model. Now, one point to drive home is that the best engineers, the engineers who are creating whole new categories of product and service, are usually very agile modelers. And so this knowledge comes to us from study by Professor Price, Dean Vojak, and Professor Griffin out in Utah. Professors Price and Dean Vojak are here at the University of Illinois. They've done work on tech visionaries, and tech visionaries are those who create large amounts of bottom line revenue from new products and services. And one of the findings of research on tech visionaries that the consummate broad spectrum modelers. They will model qualitatively, quantitatively. They will model however they need to bring a new product to life. And so they're very good at making this match between model cost and model accuracy as required to do what? As required to make some new product come to life. Now, a key distinction in modeling is between those modeling things that we're imagining and those that already exist. So in analysis, we're usually modeling things that we already know about. So we might be modeling a transmission or an automobile, or we might be modeling an airplane. So we know the configuration, and so our modeling job's a little bit easier. But when we want to model something imagined, oftentimes our knowledge is of a very rough sort. And so the key there is to actually figure out what it is that we're trying to create. And so oftentimes that argues for models that are more to the left. That is, models that are more qualitative than quantitative. And so category enhancement can oftentimes be about very accurate models, a la Newton's laws and Maxwell's equations, and models in new products are often to the right. So let's go back to the tortilla factory and see if we can model a problem that we had there. Recall that in the tortilla factory we had the situation where excess flour would burn in the ovens and then fall onto the tortilla and then be mistaken as mold, be mistaken as a product defect. Well, how do we model that? Can we use Newton's laws? Can we do flour physics? Well, it seems like a bit of overkill. And in fact, where we'll draw from here is to think in terms of argumentation theory. In 1958, Stephen Tolman wrote the book, The Uses of Argument. And since then, many people have adopted his framework as a model of how human beings make arguments. So, going back to Aristotle started the movement off with formal logic. But that logic had kind of an inhuman form to it. It was all about the form of the argument and less about the content. Tolman brought the content back into reasoning and gave us a model of arguments that is helpful for us to understand engineering modeling. Now, in formal reasoning, we have things like modus ponens. If P then Q, P is true, therefore Q is true. So this is the method of mathematical logic and formal reasoning. But notice, once the premises and rules are in place, formal logic is merely a mechanical device. In Tolman, we have something like if P then Q, but with some real-world adjustments. So Tolman argues from grounds, why is it that we believe something, to a claim. So that's like going from P to Q. But and that goes through what is called a warrant. A warrant is a statement that justifies the grounds as a basis for the claim, and warrants can be things like generalizations, analogies, causes, signs, authority. So the reasoning going from G to C can be less than certain and can be based on reasonable inference, not absolute perfect inference. Grounds and warrants can have backing. That is, why is it that we believe the grounds? Why is it that we believe the warrant? So we can imagine any support, a specific instance, statistics, testimony, and so forth, that provides specific data to believe the grounds or the warrant. And then we can qualify the claim with words like certainly, possibly, probably. So in other words, we can give some indication of how reasonable it is to expect the grounds to lead to the claim. So in this way, we connect formal reasoning to a kind that seems more human, that seems more like the kind of reasoning that people actually do. So let's go back to the tortilla problem. So what were our grounds? Well, our grounds were that dusting flour is then spread onto the moving dough on a continuous tortilla line. That's sort of where we start from. Our warrant is that excess flour can become airborne and burned in the oven deposit on the tortilla, and that comes from experience. Our claim is that burnt black flour deposits are mistaken for mold and result in quality complaints. How often does it happen? Sometimes. And our backing for this all, the backing for the warrant, is a client story and the fact that increased flour typically results in increased problems with these spots. So we can see how we can use models like this in an engineering problem to understand how it is that we do plausible reasoning. Now, one of the things that's very interesting, going back to the economic framework that we introduced earlier, is that in resource-limited environments, we often face a decision whether we should improve the warrant or the backing or work on just solving the problem. And it's a difficult choice. You might assume, if you assume the correctness of the warrant and backing and you're wrong, you need to ask yourself whether that will prevent you from solving the problem. In this particular case, in the tortilla problem, the students took the explanation that we gave previously as true because it didn't really affect the truth or falsity of the investigation. It was good enough. They spent their time on other aspects of the problem. So engineering students seem convinced, because of the nature of their education, that math and physics are the only real tools of engineering. Real engineers, however, use a broad spectrum of models from the qualitative to the quantitative, and that the economy of modeling is what separates good engineering practice from trying to be more scientific for science's own sake. Engineers are always in a resource-constrained environment. We also introduced Tolman's model of arguments to help us unify our thinking about engineering models. The bottom line here is that modeling is a critical engineering activity, but that we shouldn't think of it only in mathematical and scientific terms. Great engineers, tech visionaries, are broad spectrum models. They use the simplest model that will advance their design objectives, and we can unify those by using Tolman's model to understand how that spectrum of models kind of comes together from the engineer's intuition on the left and Newton's laws on the right.